Good morning, everyone. Today we are talking about similar figures and proportions. And even though proportions come second in the title, we're going to start out by defining that because we're going to build on that for similar figures. Proportions are two equal fractions, or technically two equal ratios. Things like 1/2 is equal to 4/8 are considered proportions. Even though they look different, it has the same relationship between these two numbers as these two numbers. And we can use proportions to draw a lot of conclusions and also to find missing pieces of information. And our most common tool for that is what's called the means extremes property. And this is probably a review for you guys, but if you know that A over B is equal to C over D, that means that, according to the means extremes property, A times D is equal to C times B. Now, this is just using our principles of algebra. You've multiplied D by both sides, so it's now by the A, and you multiplied B by both sides, so it's now by the C. And it's just saying that these two relationships are both equal. And we can see that with our example of a proportion right here. Were I to do the means extremes property, I end up with 1 times 8 is equal to 4 times 2. And 1 times 8, of course, is 8. 4 times 2 is 8. So, hey, that checks out. It's definitely a good example of where this works. Now, while that's probably a review, where it comes into play in geometry is that when we're dealing with similar figures, corresponding lengths are going to be proportional. And similar figures are figures in which you have basically the same figure, only it's undergone a size change. So you'll notice that all of the angles are going to be the same degree. So these two figures, they look the same. They have like the same sort of angles. You can also see that it has corresponding sides and points, so nothing gets really left behind. It's just undergone a size change. So just keep that in mind when we're talking about similar figures. They've undergone size changes, and the only thing that is different about them is that the lengths are now proportional instead of equal. Or the sides are now going to be somewhat similar, but they are no longer congruent. So if we want to practice with the means extremes property, this is where you're most often going to use it. You're going to set up these ratios and with them solve for a missing variable. So for instance, if I gave you this proportion, 24 to 30 is the same as 50 to what? You could then use the means extremes property to say, well, that means that 24x is equal to 30 times 5, which means that we can solve for x by multiplying 30 times 5, which gives us 150, and dividing that by 24. So we end up with x is equal to 6.25. Should you want to check it, just drop it back into the original. So here I can take 24 divided by 30, and I'll end up with a decimal value of 0.8. If I have done the work correctly, 5 divided by 6.25 should also give me 0.8. And sure enough, it does. So that means we're good to go. And I do recommend, if you can, always go back and put those numbers in to make sure that your answer makes sense. So let's put these concepts together, and we are going to find missing lengths assuming that the figures are similar, and that means that all of their lengths are proportional. So you can see here I've already marked which sides are corresponding sides, which means these are going to be the sides that are proportional. And one thing that I also did is I labeled one of these I and one of these P for pre-image and image. And I don't actually know which one is pre-image versus image, but I like to label them anyway, and it won't matter which one's image or pre-image in this case. The reason why I like to label them is while these things are proportional to each other, if you accidentally flip-flop one of them, then it's going to give you the wrong answer. And here's what I mean by that. You're saying that there's a relationship between the pre-image and the image. And the relationship here needs to be consistent. So if I say x is proportional to 8, then what I have to say with the second one is 7.5 is proportional to 5 in the same order. So in other words, in order to get from 5 to 7.5, I'd have to do the same thing to get from 8 to x. And that's where it's nice to have it labeled so that if you look across, you can say, okay, all of my pre-image lengths are in the same position in my fraction. So pre-image here should be x and 7.5 along the top. And all of my image lengths should be on the same position as well. So 8 and 5 should be along the bottom of my fraction. If you accidentally flip-flopped one, it just gives you an easy way to check and see that that has happened. By the way, notice that it won't matter if both of them are flipped. So had I switched this so that I had the pre-image over the image, I'm going to end up with flipped fractions, but in the end, all of my pre-image things are together, all of my image things are together. And when I use means extremes, I still end up with my 8 times 7.5, 8 times 7.5, and x times 5, x times 5. So don't be afraid of which one's your pre-image versus image with solving for lengths. It won't matter in this case. Here I can use my means extremes to solve this. 8 times 7.5 is not what I just typed in. So 8 times 7.5 gives me an answer of 60, and that's equal to 5x. Divide both sides by 5, and you end up with an answer of x is equal to 12. And that does make sense in terms of answers, because notice we are getting larger as we go from here to here. 5 turns into 7.5. But we're going to be about 1.5 times as large. You can see it makes sense that you're not quite doubling it, so I'm not quite to 16, but somewhere in between. Now in this next one, what throws some people off is that there are tons of things to choose from. But it turns out you don't even need the means extremes property for this. You could probably figure it out without it just by looking at the pattern. So here I know that 3 corresponds with 6, so that means they went from 3 to 6. Well, that means they doubled length. Is that consistent? Well, here they went from 2 to 4, so they've doubled their length. And here they've gone from 4 to 8 and doubled their length. That means when they started with x and ended with 5, they doubled to get 5, so x should equal 2.5. So it's okay to solve it that way. If you're like, no, I can figure out the relationship between these, and I can see it without having to do the math, that's okay. But I want to show you that it will work to get this 2.5 using any of the other proportions. So I'm just going to call one my pre-image and one my image. And I'm going to drop in p over I. And what I'm going to do is I'm going to focus first on the length that I want. So say I didn't know that this was 2.5. That means that x is going to be proportional to this length of 5. So x over 5 is going to be equal to some of these other proportions. Now at this point I can pick any other proportion that I want. So I could look at 4 and 8, 2 other proportional sides, and put those pieces of information in, 4 being on top because it comes from the pre-image, and 8 being on the bottom. Once I have this, I can solve. And I get 8 times x, or 8x, is equal to 4 times 5, or 20. Divide both sides by 8, and you get x is equal to 2.5, which is correct. Now, I could have done the same thing with 2 and 4, and it would still give me 2.5. In fact, all of these lengths are proportional to each other, so I could fill in all of my fractions as equal to each other. And you can see that that makes sense because these are all variations of the fraction 1/2. Okay, so I am going to skip that bottom one there, and we're just going to look at one of the word problems that can come with proportions. So for our word problem, what we're going to look at is a scale model, and a really famous one. This one is given from Tsar Nicholas II of Russia to his wife, and he gave her a scale model of the Alexander Palace that's made in gold. It's so beautiful. I got a chance to see this one in person and was just blown away by this tiny, tiny, but incredibly detailed palace that's inside of there. And this is apparently to scale. So that means that this 30 millimeter by 65 millimeter little palace, you might want to look up a picture of this. It's just really pretty, and this one's not really coming through, is just like the actual one. And they made it to a scale of 13 over 24,600, if this question can be believed, which maybe you could fact check that a little bit. If this is true, we can find the dimensions of the actual palace using only this little picture. And in this picture, we know that the gold building is 30 millimeters by 65 millimeters. So if I want to find the dimensions, it means I'm going to be looking for two lengths. And so I'm just going to label them X and Y. And since I have two things I'm looking for, it probably means I'm going to have to set up two different equations in order to solve, because you can only solve for one variable at once. Now I've already written out my proportion, the relationship between the scale model and the palace. And I've decided to put the scale model on top, but like I said, it doesn't matter if you flip-flop these, provided you stay consistent. So here, since my proportion is 13 over 24,600, 13 is obviously referring to the smaller thing, the scale, and our large number to the full palace. So I have to make sure that when I drop in my number 30, it stays with the scale side. And X here is the corresponding length in the actual palace. This lets me use means extremes, so 13x is equal to 30 times 24,600. And when I solve this, I end up with an answer of x is equal to 56,769.231. So with this, I have one of my lengths already figured out, but I still need to figure out the other one. That means that all I need to do is basically do the problem like I did it before, only replacing my 30 with 65 and my x with y. So I'm going to start again with this proportion and line everything up very carefully. My scale is on top, my palace is on the bottom, and here I end up with 13y is equal to 65 times 24,600. So if I do 65 times 24,600 and I divide that by 13, I end up with y is equal to 123,000, which is a pretty stinking huge number. Now, just double check that your proportions here also make sense. Notice that the original ones were 30 by 65, and now I'm saying that this is going to be 56,769 by 123,000 over here. So it has doubled the number plus just a little bit more, and that makes sense. I went from 50 to double that. This is over 100, but not hugely over 100. So my answer seems to be consistent. Now, do keep in mind that in the proportions here, we are talking about millimeters. So if you wanted this in meters, you could just divide both sides by 1,000 to get a better idea as to what that might look like. And we're going to stop at this point. Tomorrow we'll have a bunch of practice problems for these. Make sure that you check over your answers for equation of a circle and size change before you stop for today. Have a great one. Goodbye.